Okay, welcome back. Now today we're going to talk about Gibbs free energy. One of my favorite shows, at least in the beginning I used to watch. I don't watch anymore, but The Big Bang Theory. And if you watch The Big Bang Theory, there's a character called Sheldon that's just really kind of a weird, quirky fellow. Apparently Gibbs was 1,000 times worse than Sheldon. No one could stand Gibbs. Gibbs did have an ally. His name was Lord Kelvin. So you probably can guess what Lord Kelvin his contribution was. But anyways, Gibbs basically he was a socially awkward person that liked to hang out in his office and do thermodynamic derivations. That's all he did all his life was sit around and do thermodynamics derivations, and he loved it. This is what his favorite thing to do, and he did a great deal of contribution to science, especially in the realm of thermodynamics. He named a variable after himself, the Gibbs variable, and Gibbs is H enthalpy minus T temperature times the entropy. And more importantly, the change in Gibbs free energy is equal to the change in enthalpy delta H minus T change in entropy delta S. And what this is that when the change in Gibbs free energy is zero, the system is at equilibrium. If the Gibbs is less than zero, if it's negative, it's going to be a spontaneous process and it's going to go forward. If it's positive, it's a non-spontaneous process and it won't go forward. So this is incredible. I mean this and the tying a G to equilibrium, we can do calculations. It's actually amazing that we can tie thermodynamics and equilibrium together. I mean, if you look at kinetics, I mean, we can't do some things right now. We have to look at them experimentally. We can't determine what's going to happen. Even with computers and simulation, we still run short. But now Gibbs energy, thermo, and equilibrium has all been sorted mostly. So this is a great thing. To give you an idea how delta G being positive, negative works, so I've written a graph here. The y-axis is the change in enthalpy, delta H, and the x-axis is delta S. So, of course, when delta H is negative, when it's exothermic, so when delta H is negative and delta S is positive, this is right here in this quadrant. So delta H is negative, delta S is positive, and that means that delta G will always be negative. This is an always spontaneous process or chemical reaction. So something like the burning of propane and oxygen. This will always be spontaneous at any temperature. The problem though is the rate. Okay, so it doesn't mean it's going to happen quickly. It just means that it's going to happen, but the time length can be a very long time length, or it can be very fast. And then the opposite is true here. If it's an endothermic reaction with the entropy going down, this will never happen, spontaneously at least. So what about if there is a entropy, if it's entropy favorable, but there's bonding holding together, this will only happen at high temperature. So it's like something like melting of solids. So what brings a solid together is the enthalpy. It's the bonding between that. And solids are more ordered, liquids are less ordered. Entropy favors liquids or gases, but what's holding it together is the bonding. You have to add enough energy to it to break that bonding, and then entropy will take over. And then this will also happen here, so where the delta H is negative and the entropy is positive. So this is kind of like the opposite, where we have liquids forming solids. So entropy is going down to form the solid, but it's exothermic. So steam condensing or water freezing, that releases the latent heat when steam condenses, and water freezes the heat, releases the heat of fusion. So that's an exothermic process, but entropy is going down. So things condense only when the temperature is low enough that the delta H being released, it will allow it to happen. And so entropy is a state function. Okay, so that means it's path independent. If you haven't taken Calc 3 or Calc 4, this probably doesn't make any sense to you, but I know that this is not a prerequisite for this class, but I like to show you that this class has applications to other classes. So not just learn about chemistry, learn that chemistry is connected to other classes, and one of them is mathematics. If the partial derivative of a function with x then respect to y is equal to the partial derivative of the function y with respect to x, that is known as an exact differential, which means it's a mother function, which means it's path independent. So entropy S, G, Gibbs energy, H, enthalpy, E, internal energy, A, Helmholtz free energy we didn't talk about. These are all path independent things. So work and heat, these are path dependent. They don't have exact differentials. But since entropy is a state function, it doesn't matter, it's path independent. So we can look at the entropy of the products minus the entropy of the reactants, and we can look at the total entropy change for the chemical reaction. And we can do that for any of the state functions, for H, for G, for E, for S. This works for all of them. It's because it's path independent. And last thing I'll talk about is a third law of thermodynamics. Perfect crystal has zero Kelvin is zero entropy. And that's because entropy, one of the definitions of entropy is Boltzmann constant natural log of the microstates. Wait a second, omega. Omega is like this. I got it upside down. Okay, so omega is the number of states. And if there's one state, and a perfect crystal has one state and it's not moving at 0 Kelvin, that means that omega is 1, natural log of 1 is 0. So S is 0. So that means entropy S is an absolute scale. So it's like Kelvin. Kelvin temperature is an absolute scale as well. So, but internal energy and H enthalpy and G Gibbs, these are all relative scales. Okay, so let's talk a little bit more about entropy. Here is the standard entropy for the noble gases. And you can see here, helium has a lower lower entropy than xenon. And this is interesting. This is one of the proofs for the quantization of space-time. So there's some debates going on right now about space-time, and we're trying to link general relativity with quantum mechanics and trying to find a way to link all these into some grand unified theory. And the question is, what is space? What Einstein refers to as space-time? And it appears to be, from what we can tell, that space-time itself is quantized. So that means that between point A and point B, there's not an infinite number of spacings you can go to. If that was the case, you would never actually get there. That's also known as Zeno's paradox. Zeno's paradox is not valid because of the quantization of space-time. And so when you have, if the spacing has only so many states, the things that have the higher momentum, there's going to be a little bit more number of states in between them. So if there was an infinite number of space points between anything, then the universe wouldn't have any structure and entropy wouldn't make any sense. So entropy is something that has arisen from the fact that space has structure. And this is also some way we can describe time. So entropy going forward is about the only thing that we can show why time needs to move forward. Why can't time go in reverse? And entropy is one of the things that's blocking the passage of time backwards. Because for every process, it doesn't, like going forward, going backwards doesn't really matter. But if you look at a long overall thing, entropy is increasing. You can't counteract that. So I think it's interesting. This is not, I know this is not in the course, but it's I think it's interesting that the entropy works this way. But let's talk about some things that are in the course about the entropy and the number of states. So we have two things. We have argon here and nitrogen monoxide. So we would expect, since argon's heavier by what I just mentioned up here, we would expect argon to have a greater amount of entropy, but it turns out it doesn't. Nitrogen monoxide does. So why is that? Well, argon has only translational energy. So remember, translational motion is like this. And nitrogen monoxide, so if this is nitrogen monoxide, it can rotate and they can vibrate as well. So it can, and so nitrogen monoxide has the ability to store energy in rotational energy and in vibrational energy alongside translational. So think of it this way. So entropy is a number of states, and say I give two people $1,000. I'll call person A argon. Okay, so person A, argon, gets $1,000, and he puts the $1,000, keeps it in cash, and throws it under his mattress. I give nitrogen monoxide. I gave her $1,000, and she puts $200 in her mattress. Then she puts $300 in the bank, and then puts $500 in the stock market. Okay, so nitrogen monoxide, putting the money in three places, has increased the number of states and possibility that the money can go to. That's higher entropy. Whereas argon, just sticking all of his money in his mattress, that's a low amount of energy. So it's a low amount of states. So because of that, because argon, and argon is just a sphere, it's just an atom. It doesn't have rotational or vibrational energy, whereas nitrogen monoxide does. So that's why there's a higher entropy. And I mentioned before about the state functions. You can do this. And delta G, total delta G, is important because it determines whether or not reactions are spontaneous or not, which we will talk about for the next chapter as well. So when we get into electrochemistry, delta G is important. That's why we're talking about delta G now before we get into electrochem. So acid rain forms in part by SO2 reacting with oxygen to form SO3, and then SO3 reacts with water to form H2SO4, which is sulfuric acid. What is the delta G reaction at 25 degrees Celsius, and determine whether the reaction is spontaneous? We already know it's spontaneous because it happens here in Hawaii, and you can tell it by if you go to a graveyard and see how corroded all the gravestones are. But let's go ahead and solve the problem. So the delta G, this is delta H minus T delta S, and our T is 298 Kelvin, which is 25 degrees. So we got to figure out delta H and delta S. So delta H, this is going to be the H, well, it's going to be, I should do the sum of the N of the pH, the products, minus the sum of the N of the reactants, H of the reactants. So this is going to be, so the products, this is HSO3 minus the quantity HSO2 plus HO2. So this equals HSO3 by the chart is minus 395.7 minus a minus 296.8 plus 0. So let me throw that in my handy dandy calculator. Minus 395.7 plus 296.8, and I'm getting these numbers from right here, by the way. And this is minus 98.9 equals minus 98.9, and this is kilojoules per mole. Okay, so then let's look at the S. The delta S is equal to the sum of the N of products S of products minus the sum of N of reactants S of reactants. So it's going to be SSO3 minus the quantity, actually I forgot the half here. I already knew that HO2 was 0 anyways. SSO2 plus S 1/2 SO2. Okay, SSO3 256.8 minus 248.2 plus 1/2 times 205.2, and let me get a little more space. All right, 256.8 minus the quantity 248.2 plus 205.2 divided by 2, and we get minus 94 joules per Kelvin. 4 joules per Kelvin. So now we gotta do Delta G is delta H minus T delta S. Delta H is minus 98,900 joules per mole minus temperature 298 Kelvin times entropy minus 94 joules per Kelvin. Let's put that in our calculator. Minus 98,900 plus 298 times 94, and we get minus 70888 joules per mole equals minus 70.9 kilojoules per mole. So it's negative. The delta G reaction at this is negative 70.9 kilojoules per mole. And since it's negative, it's spontaneous. So the reaction is spontaneous, it's yes. So this is our delta G reaction. And since it's negative, so if it's negative, it's spontaneous. Positive is non-spontaneous. And 0, it's at equilibrium. All right, why don't you try this one out? So 2 calcium plus oxygen makes 2 calcium oxides. There is the, I've already calculated the delta H and delta S for you. Just tell me the delta G reaction. Oh, I've already forgot to erase it. The answer is C. So the way you would do this is plug in delta H minus 1269.8 times 10 to the third minus 364.6 minus a minus times 298. That should give you that answer there, like that. Okay. So let's talk a little bit more about Gibbs free energy stepwise. So if you notice, these are exactly the same for H enthalpy. Okay, so if a chemical equation multiplied by some factor, delta G is multiplied by that same factor. So if you get so much energy off of 1 gallon of gasoline, if you double the amount of gasoline, you double the energy. If you have it, you have the energy, and so on. If a chemical equation is reversed, delta G changes sign. The amount of energy that it takes to create sugar from light and carbon dioxide and water and photosynthesis is the same amount of energy that you get when you burn sugar in the presence of oxygen. If a chemical equation can be represented by a series of steps, then delta G for the overall equation is the sum of the free energies for each of the energies of the reactions for the step. This is known as Hess's law. And if you took the first semester Gen Chem with me, you know that I covered it, and it should have been covered in your section as well. So let's do Hess's law to solve this. What is the Gibbs free energy for this equation? 3 carbons plus 4 hydrogens makes propane, C3H8. What I do, first thing I write is write G1, G2, G3 for each of these. And then when I write the equations, I need to decide if I need to flip them or keep them the way they are. In the first equation, we have C3H8 as a product. So I need to switch it on the other side. So I have 3CO2 plus 4H2O goes to 5O2 plus C3H8. Okay, and carbon is on the right spot, and so this is minus G1. So minus because I flipped it. Carbon plus oxygen goes to CO2. This is G2. Then we have 2 hydrogens plus oxygen makes 2 waters. And this is G3. So now the next thing I do is I need to look to see, I need to balance I want to get this equation. This is what I'm looking for. And so I need to have the right number of reactants. The other thing I can do is I can look to get rid of intermediates. I mean, oxygen, carbon dioxide, and water. I need to get rid of these. So in your logic, you can try and get rid of those, or you can get the reactants. I think in this case, it's easier to get rid of the reactants. So for the first one, I'm going to multiply it by 3 to get because I'm looking at the 3 carbons, and I also need 4 hydrogens, so I'm going to multiply this one by 2 to get that. Now I'm going to sum these up, and let me look to see what can be canceled. The 4 waters can be canceled. The 3 CO2s can be canceled. And then 3 plus 2 equals 5 O2s. So these 5 O2s here can be canceled with this 5 O2. Okay, so, and when we do that, we are left with 3C plus 4H2 makes C3H8. And we have minus G1 plus 3G2 plus 2G3. So let's just plug in the numbers. So we have positive 2074, sorry. 2074 plus 3 times minus 394.4 plus 2 times minus 457.1. And then we put that in our calculator. So solving it, we get negative 50.4, put it in a calculator. So that's how I do a recap with this one. So how do we get the delta G reaction? We apply Hess's law. So what I do is I take the first equation, I flip it because C3H8 is a product, and I want the products on the right, and I want the reactants on the left. Equation 2 I leave as is. Equation 3 I leave as is because carbon and hydrogen are both reactants. Now I need 3 carbons, so I'm going to multiply the first one by 3, and I need 4 hydrogens, so I'm going to multiply the second one by 2, and I generate the original equation that I want, and then I have to have the opposite of the first gives energy 3 times the second and 2 times the third. In doing so, I get minus 50.4 kilojoules per minute. It's going to kilojoules per mole. Okay, and this is the second time you've seen that concept. Hopefully, I don't do a chem quiz on that because I assume that you've already mastered it in the first semester as well. But I'll talk about it again here. Okay, so let me talk about reversible processes. So I mentioned the passage of time, each incremental step, it appears to be completely reversible. So if I have a piston and I have gas, if I take a little grain of sand off, the piston's going to move slightly up. If I put a grain of sand down, it's going to move slightly down. So if I really, really slowly move the sand, I can get the gas pressure to go up, and then I can add sand and get it to go back and go down. So this slow moving process, and assuming no friction loss to the wall, I can have a completely reversible process. Truth of the matter is nothing is reversible. So it's really going to be irreversible. Everything is irreversible. And but if you look at the overall process, you're losing energy because of entropy, because there is friction against the wall. There's all sorts of heat loss through the container, so it's not really a reversible process. And the way that we get around this is that we say things are reversible, then we multiply it by a fudge factor, and that's the irreversible heat transfer. So you'll learn about that in future classes if you study more thermo. Okay, so thermo is thermodynamics. And what about, we've been talking about standard states at 25 degrees Celsius. What about non-standard? So the way that we get non-standard is the change of Gibbs of the reaction or process that's non-standard is equal to standard state plus RT natural log of Q. Q is the reaction quotient. R is a gas law constant. It's really it's Avogadro's constant times Boltzmann constant. That's what R really is. And temperature, T is temperature in Kelvin. And this graph here shows, so the y-axis is free energy, x-axis is partial pressure of hydrogen. It depends on where you're at in this graph. If there's too little water vapor, so if water vapor is too little, the water will evaporate. If there's too much water in the air, the water will condense, and it'll keep on going until it reaches equilibrium. Of course, the rate in that is unknown, and it's not known by thermo. Okay, so let's calculate delta G. under non-standard conditions. So we have this equation, 2NO plus O2 makes 2NO2. The standard Gibbs is given at negative 71.2 kilojoules. What is the Gibbs the Gibbs change and the change in Gibbs free energy for the reaction under these conditions? And so we have to look at the Q. The Q is going to be the pressure of NO2 squared and divided by the pressure of NO squared times the pressure of O2. So let's put this in here, apply the equation. Minus delta G is minus 71. I always write this out because I always forget. Joules plus R, 8.314. Temperature 298. So this is joules per mole Kelvin, 298 Kelvin. Natural log of Q, NO2, so this is going to be 2 squared over 0.1 squared times 0.1. Oh, that's 4,000, right? So 2 squared is 4, and over 0.001, this is 4,000. Okay. So let's go ahead and put that in the calculator. Okay, I'm back. I put the numbers in a calculator, and this is what I got. I got minus 50.7 kilojoules, and that's lower than the minus 71, so it's less spontaneous, and that's what I put in my calculator, so you can see and follow along. So recap with this one. This is a non-standard delta G, so we apply the delta G is delta G0 plus RT ln Q. We state our Q, we calculate it out, and we throw it in the equation, and we get a number that's lower than, it's still spontaneous, but lower than, it's less spontaneous than the original, or than the standard state. So why don't you try this one out for this equation. Methanol liquid to methanol vapor, the delta G is that. What is delta G at 0.2 atmospheres? So a little hint with this, the Q is going to be 0.2 atmospheres because that's just the methanol vapor. So why don't you try this one out? So hopefully this is the answer that you got from that. Okay, so moving on, I mentioned this before, that we can tie in Gibbs free energy to equilibrium. And this is amazing. We are tying in thermo and equilibrium together. So delta G0 is minus RT ln K. So remember when delta G0, when Gibbs is 0, we're at equilibrium. So our standard states is minus RT natural log of K. K is the equilibrium constant. Or we can rearrange for K. K is minus delta G, e to the minus delta G over RT. So this is amazing. Look at the energy. Looking at the energetics, we can figure out the equilibrium. This is so cool. I know thermo is pretty not so dazzling like other things, but this is amazing that we can tie this together. It's a great thing for chemistry and technology. So calculate the equilibrium constant for the following reaction at 298 Kelvin. And so that means that we don't have to do this in the laboratory. We can go to the library and calculate this out. We don't even have to go to the library anymore. We can look it up on the internet. And then you can apply your equations. Okay, so the delta G0 reaction is going to be the sum of the N of P, G of P, minus the sum of N of R, G of R equals, so products, it's 2GNO2 minus GN2O4 equals 51.3 times 2. I should put the 2 on the other side. 2 times that minus 99.8. And what does this equal? Let's figure this out. Two times 51.3 minus 99.8. This is 2.8 kilojoules. Okay, so then we have K equals E to the minus delta G0 over RT. equals E to the minus 2,800 joules over 8.314 joules per mole Kelvin times, oh, this is joules per mole, times 298 Kelvin. So the units all cancel out, and let me put that in my calculator. So here is the numbers I get in my calculator, and this is what I put in there. Don't forget that I always write out, whenever it says kilojoules, I always write out the 3 zeros on it just because I always forget. So if you want to start doing that habit too, that wouldn't be a bad habit to learn. But the answer is 0.3.2. So look at that. We can get the equilibrium constant. Can you imagine how difficult it would be to measure this equilibrium constant? That would be a very difficult experiment. I'm glad we can just look at some numbers in a book and get it. Okay, so that is the end of this. Let me show you how we get some of these equations. So we have another 2-point form. So delta G0 reaction is minus RTLNK. And this also equals to the standard, so I'm reading the top line here, the standard enthalpy change minus a T delta S change. And let's take the natural log of both sides. And then we can, so take the natural log of that, and then, well, I should say that, I'm sorry, we take this equation, multiply it by minus RT. And we get this equation here, and then we can take ln, and we can take K2 and T2 and K1 and T1, and when we do this, we can subtract them, and we get rid of the delta S over R, and then from that we generate this equation here like this. So I was just trying to prove that for you if you're wondering where these derivations are, how these equations are derived. I just go ahead and give them to you. So I'll give them to you on some sheets of paper. But if you're wondering how they're proven, that's it. But there's no example in the book on this problem. But that's it for thermo. We will use these thermodynamic concepts, not initially. We're going to learn how to balance equations in the next chapter. We'll start off with the next lesson. But then we'll use thermodynamics again when we talk about electrochemistry. So I will see you then.